Hey everyone, so this is going to be the first video in the series I'm making about the gas chapter from my textbook, which reference, I believe it's chapter 5 in my copy of Zumdahl 8th edition. Just in case you didn't see that intro video that I made. Yeah, I don't want to make this video super long at all. Like ideally I'll make these videos about like 15 to maybe like 20 minutes long. I'm pretty sure when I was like going through like the planning part, like I'll probably need about like 3 to 4 videos to get through this chapter. And I just want to say that too, like there are a lot of really cool sections in the chapter, like about real world applications of gases and like all the cool math that goes into like how these scientists were able to figure out their equations and like what went into actually like doing the experiments, which I think it's cool and all, but it's not really important in terms of like understanding what the equation is, or even like it's probably not something you'd ever be asked on an exam. So I'll just leave those for like if you want to read them, like please go for it. But honestly, like I'm gonna try to put in these videos like all the things you might see on the exam, or just like the things that people will commonly get confused on or like make mistakes on with these equations. So I'll do that to keep the videos a bit shorter then. Um, and yeah, so with that said, I'm probably just gonna like jump right into it. So with the gas laws, we basically start with four main equations. These are like the four like early equations that scientists first discovered or like postulated about gases. And then from these four, basically where you'll make the two equations that like you'll use for everything. Like there's the combined gas law and the ideal gas law. Those two gas laws are like amazing. They will do all the work for you once you get like into high enough chemistry. But at least for right now, knowing these four more earlier equations is still really helpful. So with that, the first law is Boyle's law. And this law basically takes pressure and volume. It understands how changing one of those things impacts the other one. So the relationship is that the initial pressure times volume of a gas system has to be held consistent to the final pressure and volume. And what this assumes is that you have a constant temperature system. So you won't be changing the temperature, you won't be making it any hotter or any colder. You're just basically expanding and contracting the gas. And if you kind of want to think about like an example to help make sense of this, I like to think about like a water bottle. So if you take a water bottle and you like twist it or like you scrunch it and like really compress it, and then you like unscrew the cap off, it'll like explode off and like a bunch of gas like mist comes out. Well, the reason that's happening is because if we take this left side to be like what the water ball is before you scrunch it, once you twist it and make it like a lot tighter, you're basically decreasing that volume. Instead of it being able to fill a whole water bottle, it's now maybe in like half the same volume. So by decreasing the volume, we need to increase the pressure then. And if you want to think about how, like, let's say P1 V1 equals just one. It just equals one to give you an easy number. If I make P2 a half, that means my volume has to be two, right? So whenever you make any sort of change to pressure or volume, the other one has to do the opposite of it. So if you double one, the other one has to go down by a half. Or if you triple one, it has to go down by a third. It's always going to have that sort of relationship where they're doing opposite things with one another. And yeah, so that's pretty much all you really need to know about Boyle's law. The next one is Charles's law. And one thing I want to say too is that all of these laws right now are basically just going to take pressure, volume, and temperature and find unique ways to relate those together, but keeping one of them constant. So in the case of Charles's law, we're going to deal with volume and temperature in this case. So you have V1 over T1 has to equal V2 over T2 with constant pressure. And this one might be a bit harder to like think about or like explain. Oh, we're in a hurry. Um, but if you basically think about it, like if you have let's say a pot of water and you set it to boil, that water is slowly going to be heating up. It's going to be like it's going to start bubbling a little bit. And eventually over time, you'll see it begin to evaporate. And that water mist is going to take up a huge amount of space compared to that small pot of water. So whenever you heat up any sort of gas, it's going to want to expand and take up more volume. Same, but the one difference here is that because it's a ratio, because it's volume one over temperature one equals volume two over temperature two, they're going to do the exact same thing when you change them. So if you double volume, sorry, let's say if you double the temperature, that leads to a double in volume. And the opposite is true. If you half the temperature, your volume is going to decrease by a half also. So this gas law, it doesn't have the opposite effect. They're both going to do the exact same thing when you change one. And yeah, so now we have Gay-Lussac's law, which if you've noticed, we've used pressure and volume together, and we use volume and temperature together. The only combination left is to use pressure and temperature. And very similarly to Charles's law, if you were to change temperature, if you double it, so if you double temperature, you're going to get a double pressure because you see them as a ratio. If the ratio is going to be one, doubling pressure on top means the temperature has to double also to keep the ratio as one then. Um, and as you'll notice here, we don't see volume in this equation. So we have a constant volume, which is a pattern you'll notice in a lot of equations as you go through chemistry. If it's not in the equation, it means it's either being held constant or for some reason doesn't actually impact the equation. So if you look at Boyle's law, there was no temperature in the equation. That's why we keep it, that's how we know it's held constant then. Or Charles's law, there's no pressure in the equation. That means it has to be held constant. Because once we start changing more than just one variable, it gets really hard to predict anything in chemistry. So we usually try to be very careful with that. And if you want an example of Gay-Lussac's law, sort of similarly to what I said about Charles's law, if you just heat up gas, so if you take like, let's say like you take like a bunch of like water in like a bottle, and you start boiling it, it's gonna want to explode the cap off. A good example is when you microwave food. Whenever you microwave it, usually take the lid off just a little bit to let the gas escape. But if you ever forget to take it off, the whole thing just explodes then. And that's because as you increase the temperature of that system, the pressure starts to increase and starts building up, and it wants to try to escape somewhere. So that's kind of a way to think about Gay-Lussac's law. And the last one is Avogadro's law, which if you know anything about Avogadro, he had a really beautiful way of studying how the molecules of some gas or the molecules of an atom or element relate to moles of an element. So what his law says is that V1 over N1 equals V2 over N2, where N is equal to moles. And just in case anyone like needs a refresher, maybe hasn't heard the word moles before, what a mole is basically the number of molecules that there are in a substance per mole. So when we say 1 mole, that correlates to 6.022 times 10 to the 23rd molecules. And this is true for any element. You know, if you look at hydrogen, carbon, iron, titanium, whatever you want to look at, this is always true for all of them. What is different though is their weight, and that's a little bit different. So I'll get more into that into the videos when we talk about like thermodynamics and other stuff like that. But at least for right now, just knowing that N is the number of moles you have and that moles is dependent on the molar mass, that's really all you need to know for right now for gases. And if you want to think about how Avogadro's law works, kind of think about it like if you're blowing up a balloon. As you begin to put more and more CO2 gas or O2 gas for when you exhale into that balloon, it starts to want to expand and take up more space. So Avogadro's law basically just says the more stuff you put into something, the bigger it has to get to try to accommodate all that stuff. And if you look at the equation, actually, you'll notice we don't have any mention of pressure or any mention of temperature either, meaning that those are being held constant in this case. You're not changing the pressure or temperature at all. All you're doing is allowing the gas to either enter or escape your container or whatever you're holding it in. So there's no changing of how hot the container is or how much pressure you're applying to it. So all that's being held constant in this case. And yeah, that's basically the rundown, the four earliest or like the simplest equations. What we have coming up now are these two equations that take everything that we've seen here and combine them. And they give you so much more freedom in terms of the problems you can work on and in terms of how complex you can do a problem or do a system now. So for those two, we have the combined gas law and the ideal gas law. And the ideal gas law is amazing. It's so cool. And it's just a really satisfying way of how all these equations come together into one equation, basically. So for the combined gas law, that basically will take all three of these first ones we looked at, of Boyle's, Charles, and Gay-Lussac's, and combine them into one equation. And that equation is P1 V1 over T1 equals P2 V2 over T2. And before I explain this, I just want everyone to keep this in mind always. What don't you see in this equation that we saw previously? When we looked at all these equations, you had pressure, volume, temperature, and eventually moles in the last equation. Of those four, which is not present in the combined gas law, it's moles. You don't see N present. So because there's no N in the equation, you have a constant number of moles. And that basically means you can change whatever you want to this container or to this system, but you can't let the gas escape. And you can't put any more gas into the system because it's not included in the equation. When we get to the ideal gas law, we finally can account for how moles impact the system. But for right now, we can only worry about changes to pressure, volume, or temperature. And that's basically it. It's kind of hard to think of an example of the ideal of the combined gas law, just because you have so many possibilities. But if you ever see an equation where you have two pressures and two volumes and like a temperature, and you have a lot of information, typically you'll want to use either combined gas law or the ideal gas law coming up. Which, speaking of, finally going to talk about it. So ideal gas law takes into account now all four of these equations. So it considers not only pressure, volume, and temperature, but also moles. So this equation is PV equals nRT. We're now have introduced a new variable. Essentially, I've introduced the R value. And what R is the universal gas constant. And I want you to please like put a star next to this or like underline it or do something because R comes up so often. It comes up with gases, with kinetics, with thermodynamics. So you really want to make sure you're using the right R because there'll be two different ones that you can use. In the case of gases, we use the R that is equal to 0.08206 liters times ATMs over moles times Kelvin. And I'll talk about units in this next slide coming up, but you really want to take note of what units you're using, since this R will give you answers with liters and ATMs, whereas the other R that I'll use in future videos when we get to the energy stuff will give you answers in joules because you want energy units, not liters or ATMs. That's not energy. And yeah, that's pretty much it for all the equations. As I said, these two are basically the ones that you will use all the time because they give you so much more freedom in terms of what you can modify or change about a system. These four are still great. And like, if you have a problem that just gives you pressure and volume and you want to know how it changes, then you kind of have to use this since there's no information about the temperature. But yeah, you kind of just use them based upon what the problem gives you. And you kind of just like go from there. So it's good to know all of them, but definitely just like write them down like a little equation sheet and just like be able to look back on them whenever you forget one or you want to make sure that you have the right one. All right, so next thing I want to talk about quickly is just the units, since units are very annoying. I've missed a lot of points on college exams because I forgot a unit or I used the wrong unit on an equation, so it happens. But there's a lot to keep straight here about the different values we look at. So pressure is probably the most annoying one, since there are a lot of units for pressure. Commonly, we'll just use ATMs, which stands for atmospheres, but there are a lot of other values you could use, and you'd be asked to convert them back into ATM. If you're wondering why it needs to be an ATM, look at the R constant that we talked about in the last slides. The unit up here in the numerator is ATMs. If I tried using kilopascals or bars or millimeters of mercury, it wouldn't cancel out properly because this R unit is considering that you're in ATMs. I'm sure there are other R's you look up that have a unit of millimeters of mercury or have all these different pressure units, but it's just easiest if you just convert the pressure you're given into the correct unit of ATM and go from there in the problem. So in terms of like the common units you could see otherwise, I'll give this to you in terms of one ATM. So one ATM is going to be equal to 101.3 kilopascals, or if you say 101,300 pascals, you could also see that, but because of how big that number is, people commonly just use the kilopascals for that unit. This is also equal to 760 millimeters of mercury, and that is also equal to 760 torr. I don't actually know what a torr is. I've thought about looking it up to read about where it comes from, and I always forget. So I might do that tonight, but I also might forget. So you just gotta know that a torr is an option for pressure you could be given. And lastly, all this is about equal to 1 bar. A bar is a little bit less than an ATM, like just a little bit. I'm pretty sure a bar is about like 0.98 ATMs. But honestly, if you're asked to work with bar and they don't give you the conversion, they probably want you to just know that a bar is like almost an ATM about. Thankfully, the rest are all pretty straightforward. Volume is always given to you in liters, or I'm sorry, I shouldn't say that. It can be given to you in anything, but you would need to use liters for the equation. Again, unless they give you the conversions, it's pretty unfair to ask you to go from like centimeters cubed to liters. So it'll probably just be given to you in like liters, or at the worst case scenario, milliliters, which, to refresh anyone, you have 1,000 milliliters per 1 liter. And next we have moles, which this one, thankfully, we have an easy one. It's just moles. You worst case scenario, since I love to talk negative, you be given it in kilograms, or you be given it in terms of the molecules of substance. That's like the worst they could do. In that case, you just need to go from mass to moles, which, just keep in mind that the moles that you have is equal to the mass of substance divided by molar mass. That's really it. Or, you can also say this is equal to the number of molecules that you're given divided by 6.022 times 10 to the 23rd molecules. These are like the two worst case scenarios you could be given. But that way you're just prepared for anything you could see on an exam or a practice problem. Now, temperature, I really want to make a note of, because I've seen so many students that I've TA'd for lose points on exams for their temperature, because you have to use kelvins. You cannot use Celsius. Even if the problem gives it to you in Celsius, it is just trying to trick you, which sucks, and it's mean that they do it, but it happens nevertheless. So if you want to go from Celsius into kelvins, what you have to do is you have to say that kelvins are equal to Celsius plus 273.15. Now, I'm annoying. I like to use like the most precise numbers for constants that you can find. Is this 0.15 the most important thing to include? Probably not. Most of you will probably just work with just 273, and that's fine. It's usually so similar that you don't get any real differences, but that's just like that way you have it in the most like exact way possible. And lastly, for the universal gas constant of R, in this case, and I want to make note just for right now, is in units of liters times ATMs over moles times Kelvin. When we get to thermodynamics, it will change, and you will instead have a unit in joules, which is fine because you'll have a different value. But just make note, you have an R value for gases and like doing volume stuff. You have an R value if you want it in joules and energy. Those are two very different R's. So just keep those separate when you get to thermodynamics. And yeah, that's pretty much it in terms of like the gas laws and all the units you need to worry about. I just want to work through like two quick problems to show you like how I approach them, and to hopefully give you a sense of what you should look out for when you work on these problems. So for this first one, we have a sample of hydrogen with a volume of 8.56 liters. So I'll write that down. You should always organize it and have like it all written down to see then what you're missing or what you need to figure out. So we know volume is 8.56 liters, and we have a temperature of 0 Celsius. Okay, that's weird. So we have a temperature of 0 Celsius, which I want everyone to go ahead. Once you see Celsius, just stop what you're doing, convert that to Kelvin always. because you never want to forget to do it in the middle of a problem and then you use it on accident. It's happened to me before. It's the worst feeling because you meant to do it in kelvins. So go ahead and convert this temperature into Kelvin, and if you do that, you should get 273 Kelvin. 273.15, same thing. Doesn't really matter. It won't impact your answer all that much. And we also have that a pressure of 1.5 atm. Awesome. Okay, and we're asked to find the moles of hydrogen present in this gas sample. So we need moles. So now we look at what we have. We have a volume, we have a temperature, and we have a pressure. What's important is that there's no change happening, right? We're just looking at a gas at what it's doing right now. So there's no need for a V1, there's no need for a T2 or anything like that. We just want an equation that takes pressure, volume, and temperature and tells us about N. So you need all four things. Which one does that? It's my favorite one. You better remember it because it is the ideal gas law, this beautiful equation. So you want to use PV equals nRT here. So we will say PV equals nRT. Personally, I like to isolate the variable first instead of just plugging in the numbers ahead of time. It just saves me sometimes from making mistakes on exams. So I just divide this by RT to cancel that out. And I get that the moles should equal PV over RT. All right, awesome. Now that we have that, we can go ahead and plug it all in. So we know that the moles of H2 should be, sorry, I'll do it like this, sorry. Moles of H2. This should be equal to pressure, which is 1.5 atm. If it wasn't ATM, remember, you got put into ATM. So if it's in bar, usually that's okay. That's close enough. But if it's in like millimeters of mercury, torr, kilopascals, any other weird ones your chem teacher can find somewhere, put them all into ATM right away. And then for volume, we have 8.56 liters. And we divide that by R, which remember, this R is 0.08206 liters times ATMs over moles times Kelvin. And lastly, temperature, which you went ahead and you did it already. So we know that this should be 273 Kelvin. If you forgot, and this is a really great skill to learn in terms of like problem solving, if you had not changed that temperature from Celsius to Kelvin, what would you have gotten here on accident? You would have gotten that there are an infinite number of moles. Because if you plug in zero into the denominator of a fraction, it's basically undefined or infinite. And it doesn't really make sense to have infinite amounts of H2 since that can't really ever happen. So that's like a good way to check yourself. If the answer just doesn't make sense, like if you get zero or like infinite, usually that's not right in chemistry. It usually doesn't happen all that much. So that's like a good way to check yourself. But anyway, if you do this math out, you should get about 0.56 moles of H2. Awesome. Good job. Um, and please, if you ever have any questions, like please feel free to leave it in the comments section. Like maybe I just like overlooked something, or maybe I didn't explain something properly enough. So please just like leave whatever questions you have down there, and I'll be happy to go back and like read through those at some point. And yes, we did that problem. Hopefully you feel pretty good about that. I just want to do one more quick one and then end this video finally. So in this example, we have diborane gas, a really cool substance, that can burst into flames when exposed to air. That's just cool chemistry tidbits when you get to OChem. It's really fun. As a pressure of 345 torr, okay, a little weird, not an ATM, a temperature of negative 15 degrees Celsius, and a volume of 3.48 liters. So I'll underline all of those. Now, before I read the rest of the problem, I want to go ahead and just convert these into values that are much easier to work with. So for starters, temperature, negative 15 degrees Celsius. We can't use that. It has to be in kelvins. So we're going to go ahead and add 273 to this. So if you do that, you should get around like 258 Kelvin. All right, awesome. We did that. Now for torr, this is why I went ahead and gave you all the units of pressure earlier. We can't use torr. We need ATMs. So to do this, we're going to take 345 torr. We're going to divide that by 760 torr. If you do that, you should get about 0.5, wow, 454 ATMs. I go out to three sig figs or three digits. You don't have to. That's just my preference. You kind of just do whatever your teacher tells you to do or whatever you feel the most comfortable doing for the most part. So that's just something for you to figure out as you go throughout chemistry. Oh, great. So we have those three things figured out for the first half of the problem. The second half mentions a change. So we are changing something in this problem, meaning ideal gas law might not be what we use here, probably will be a different one. So it tells us that the temperature is negative, sorry, not negative, it's 36 degrees Celsius, and that the pressure is 468 torr. Okay, one thing to note, what information were you not given here at all? You weren't told about the moles of substance. We have no clue how much of this diborane there is, meaning it probably doesn't matter. And that's more proof as to why we probably won't use ideal gas law, because that involves the moles. We have to know how many moles there are in order to proceed. Now we could figure that out. We absolutely could. We know what PV and T are. All right, we already have that. We can figure out what N is, but we might not have to, because that involves just more work. So this is a point where you either choose to work in a way that feels comfortable to you and that you can use PV equals NRT. Please do it. If you use PV equals NRT, you take these first three conditions, figure out what N is, and then once you have N, you bring that down here and then figure out what the volume is. You can absolutely do that. I don't mean to say you can't do that, but instead, what I want people to kind of understand is that it's sometimes easier just to take a step back and see what you're given and work with that. All right. Maybe we did need N. That's totally fine. We don't know that right now. The best thing we can do is take a guess from what we know and see where that goes. So what I know is that we have a P1, a T1, and a V1. And we also have a T2 and a P2. All right. That looks a lot like the combined gas law of P1 V1 over T1 has to equal P2 V2 over T2. That's what it looks like to me. Maybe we will need moles at some point, but for right now, this at least to me looks like a much easier way of solving the problem that goes through less steps. Again, nothing wrong with ideal gas law. If you think that's what's easiest, please do it. But I just want students to see you don't always need to rush in with what you see right off the bat or what you think is easiest. Just take a second and just try to remember all the equations you know and just think about what one can be done in the fewest steps. So what we need to find here is V2. So I'm going to go ahead and isolate for V2. So I'll multiply both sides by T2 and I'll divide by P2. So if I do that, we find that V2 has to be P1 V1 times T2 divided by T1 and P2. Just gonna fix that. Okay, there we go. So if we do that, we find that V2 should be equal to 0.454 ATM times 3.48 liters times 258 Kelvin. Now we divide that by the temperature and the, oh, nope, sorry, wait, I made a small mistake here. So we have T2 on the top. This is why you should always stop and see what you're doing. We have T2, which we need to convert firsthand. So I'm gonna go ahead and move this over a little bit. So this temperature here, remember, we always add 273 to it. So if we do that, we should get that the temperature is 309 Kelvin. And then for this pressure, we're going to do the same thing we did above. You take the pressure in torr and you divide it by 760 torr, and that gives you it in ATMs. So I'm going to go ahead and solve for that too. And that should be equal to 0.616 ATM. Okay, awesome. Now we have all the information, most importantly, in the right units. So now I can take those, plug in T2 on top here, which is going to be 309 Kelvin. And now I take temperature 1, which is 258 Kelvin, and multiply that by pressure 2, which is 0.616 atm. All right, awesome. We did that. Now you just go ahead, do all the annoying dumb math. And then once you get that, you should get that this volume ends up being about 3.072 liters. And now we can kind of look and see what we got. What we find here is that the volume went down a little bit, even though we raised the temperature. You know, your temperature went from negative 15 Celsius, pretty cold, to 36, pretty warm. So like it's a little weird that volume still went down, knowing the relationship we talked about earlier, that if you increase temperature, volume should increase. But keep in mind, we also did increase the pressure, right? We increased the pressure from 0.454 atm all the way to 0.616 atm. So what this problem highlights is how things can kind of like contrast, like fight in chemistry. You have this tug of war between an increase in pressure, which should decrease volume, while also having an increase in temperature, which should increase the volume. So they're kind of fighting each other. And what you find is that the change in pressure was like more significant. It was to a greater extent to where the volume overall decreased from this 3.48 liters down to 3.072 liters. So just something cool to notice. I'm gonna stop the video there. I did end up going a little bit longer than I expected, so I think probably this will be about what the format is. So I think this length worked. I'll do about like 15 to 20 minutes of like lecture explaining things, and then probably just like 10 to 15 more minutes of working through problems, since I don't think it's smart to separate them into two different videos. I think it's better just to have them all in one. So I'm gonna keep figuring out how this whole format thing will work. But yeah, thank you so much for watching. Hopefully you got something out of that. If you have any questions about anything that I talked about, anything that was still confusing, or maybe anything that I did wrong that you noticed, like please leave a comment and I would love to respond to that. But yeah, just thank you so much again and hope you have a great day.